Okay, so in this video we're going to look at 2013 higher level paper question 8. Particularly just this little piece here about sketching the voltage time graphs. So the first few parts there are pretty self-explanatory. You name the parts F, G and H. F is the iron bar of the transformer. So they'll accept iron core or transformer in the mark scheme. G is our semiconductor diode, and H is a parallel plate capacitor, or just capacitor, I suppose, is the safest thing to say. To describe the function of G in this circuit, the function of our semiconductor diode is to only allow current to flow in one direction. Now the mark scheme is looking for you to say that it is going to act as a rectifier. So something that converts alternating current to direct current. So we have an alternating current induced in the coil here, and it'll basically turn that into a direct current by only allowing it to flow one way. And then we get onto the hard part, the input and output voltages for this transformer setup. It's more than just a transformer, right? We have a transformer here, which induces a G and EMF in the secondary coil. But then we also have a diode here, which is going to only allow current to flow one way. And we also have a capacitor here, which I believe is going to be used to smooth out the fluctuations in the DC current. So the first thing they want us to do is plot the voltage over time for the input. That one is actually pretty easy, right? We're going to have our axis here. This is voltage. Right, there's our voltage, and we can label that positive or negative. I don't think they're going to really care if we do or don't. And then this axis is time. So because it's alternating current for the input voltage, what we're going to see is a classic alternating current sine wave type thing, where it goes from a peak positive voltage to a peak negative voltage, and follows a sine wave the whole way along. The peaks should be pretty consistent. I know I haven't done a great job on that. And the same thing with the troughs. But yeah, ideally they will be consistent the whole way across. Hopefully you find it easier to draw it out on your own copy. To look at part 2 then, I think that what we're going to do is just try and look at it in stages, right? So what we'd expect to see is a very similar looking graph where you've got voltage on our y-axis and time on our x-axis. Now we know that the induced EMF is going to try and oppose the magnetic flux change that caused it. So this should basically be out of sync with the original one. So we'll end up with something that is basically the same shape, but the current goes the opposite direction, right? I don't think you're going to gain or lose marks here on that, to be honest. The mark scheme doesn't seem to care. They look for the correct shape of the output voltage. Now, when I originally read the question, I kind of interpreted it as being like this, but then thought that's too easy. So then I looked a little bit closer, and what they're asking is the output voltage across XY. So it's not just the voltage induced during the EMF, it's the voltage at XY. And I might actually say as well, for a transformer, normally you'd expect the output voltage to either be greater or smaller than the input voltage. So I'd maybe, if that was the case, make an effort of like drawing smaller troughs and peaks. So I tried to look into that, and the number of coils here you can count 1, 2, 3, 4. It's the same as the number of output coils or secondary coils, 1, 2, 3, 4. So the voltage should be the same. So I try and draw these roughly to the same scale. Again, it doesn't seem like you're going to lose marks for that according to the mark scheme though. So yeah, instead of just looking at the induced EMF across this coil, which would be too easy, I guess, they want you to answer a much harder question. What is the induced voltage across XY here, the potential difference between X and Y? So the first thing I'd be thinking at then, or the next thing I'd be thinking about is, right, I've got two components here. One of them is going to be a diode, and the other one is going to be a capacitor. So I can think about what the effect of each of those is going to be individually. So let's look at the diode first of all. So our semiconductor diode is going to allow current to flow in one direction. So essentially, charge is only going to be able to flow to these 2 points half of the time. So we lose any potential difference that's going in the opposite direction, which looks pretty bad and looks like a quite unusable and unstable source of electricity, and it is at the moment. Right, I'll draw another one there. So that's pretty bad. But that's what will happen if you were to just attach up a diode there. Potential difference is able to be formed across X and Y, but only in one direction. We're missing basically half of the voltage. So pretty bad. But what we do also have in here is a capacitor, and its function is to store charge. So that makes the whole thing a little bit more useful. If potential difference builds up, a positive potential difference between X and Y, then when an opposite potential difference builds up and current isn't able to flow through the circuit, there's still then a charge across the two plates. So that charge will discharge, and it'll basically kind of top up the potential difference, or the charge that's made available to X and Y in the meantime. So what we'll see is a peak EMF or peak voltage, and then it kind of decays with time as the capacitor discharges, and then it goes back up to peak again, and then decays with time, if that makes sense. And then if we wanted to follow this back in time, to be an invisible peak back there somewhere too. So I think that will be the shape of the thing. I think probably if you do it like this, you will get full marks. But if I wanted to make it super nice and well presented, I would probably try and just get rid of these lines, because they aren't actually representative of the potential difference. So something like this and this. Yeah, so it looked like that basically. And again, that isn't necessarily representative of what's going on there. Right, so there's quite a few steps to get to that. So I think basically if you twigged that they were asking you about the potential difference between X and Y as opposed to just the induced EMF across the secondary coil, then you would have something hopefully that looks like this. And that will get you almost full marks. You get your 3 marks for having your axes labeled properly on one of the graphs. You get 3 marks for the input voltage being alternating, and you get basically 6 marks for this. You would get 1 mark taken away for not having the smoothing effect of the capacitor, but yeah, I think that would be pretty hard. I wouldn't expect many people to get that fully, to be honest. But even if you get something like this, I think that would be great. But anyway, if it does come up now, you'll know it.